Welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. This video focuses on CPU billing, specifically addressing the CPU hours deducted from your quota for a job on the compute nodes. To illustrate, let's request an interactive job with a single CPU core and 5 GB of memory, identified as job number 11, 248943. This task will be carried out on the C559 node. I'm eager to understand the impact on my CPU quota when requesting 1 hour of wall time. To view the billing information for a particular job, you can use the Linux command SQ with the J option, followed by the job number and the format option. Executing this command reveals that the job requests 1 CPU core, 5 GB of memory, and 1 node, with billing equal to 1. This implies that the CPU time aligns with the wall time, and 1 CPU hour will be deducted from my CPU quota. I can also obtain this information by using SQ with the U option, followed by my username. On a Linux cluster, SQ is short for show queue. It is a command used in the Slurm workload manager to display information about jobs in the queue, including their status, node allocation, and other relevant details. Let's request another interactive compute job with a single CPU core and 10 GB of memory. How many CPU hours will be deducted from my CPU quota when I request 1 hour of wall time? We can see that the job requests 1 CPU core, 10 GB of memory, and 1 node with billing equal to 2. This indicates that the CPU time is twice the wall time, resulting in a deduction of 2 CPU hours from my quota. It's important to note that the requested memory affects CPU time, and asking for more memory than necessary leads to the wastage of CPU hours. As mentioned in our first video, the Linux command "L" is an alias for ls, with the L option. Similarly, we can create our own alias for the billing. Let's navigate to my home folder using the cd command and execute ls with the A option. This will list all files and directories in my home folder, including those starting with a dot, usually hidden when using the "L" command. Now, let's take a look at the .bash rc file using the Emacs editor. Within the .bash rc file, I've created an alias CPU bill, which is a concise version of the billing command we've been using. From now on, we can utilize this command. When you edit the .bash rc file for the first time, use the Linux command source to activate the changes. Without this, the modifications won't take effect until your next login to Saga. Let's request 1 GPU with 1 GB of memory on the Axel nodes, and then utilize our new alias CPU bill. Currently, the billing factor is 6, signifying that the CPU time is 6 times longer than the wall time when asking for 1 GPU on the Axel nodes. Let's request 1 GPU on the A100 nodes using 1 GB of memory. Now the billing factor is 8, signifying that the CPU time is 8 times longer than the wall time when requesting 1 GPU on the A100 nodes. It's important to note that this relationship can change if you request more memory. Now let's request a job with 8 CPU cores and 4 GB of memory, and then utilize our new alias, CPU bill. The billing factor for this job is 8, indicating that the CPU time will be 8 times longer than the wall time. This is expected as we are requesting 8 CPU cores, and typically the number of CPU cores directly influences CPU time. However, it's important to note that this relationship can vary with memory usage. Let's request the same job as before, but with an increased memory allocation to 5 gigabytes. By using the alias CPU bill, we can observe that the billing factor has increased to 10, indicating that the CPU time is now 10 times longer than the wall time. This highlights the impact of memory on the CPU time. Requesting the same job with 10 gigabytes of memory now results in a billing factor of 20, indicating that the CPU time is 20 times longer than the wall time. Comparing this to the previous instance where we requested 4 gigabytes of memory giving a billing factor of 8, it's clear that the billing factor increases with higher memory usage. Therefore, it's crucial to avoid using more memory than necessary to prevent unnecessary consumption of CPU hours from your quota. Each normal compute node has 192 gigabytes of memory. If we divide this memory by 40, we get 4.8, and by 52, we get 3.7. To maintain memory balance, it's advisable to request around 4 gigabytes per CPU core for a job on the normal nodes. Requesting more than 4 gigabytes would classify as a high memory job, while asking for less than 4 gigabytes would be considered a low memory job. It's advisable to refrain from requesting high memory jobs unless absolutely necessary. Opting for memory-balanced or low-memory jobs helps prevent the unnecessary consumption of CPU hours. For additional details on CPU billing, refer to the online documentation. If you find yourself unsure about CPU billing, utilize your newly created CPU bill. In the upcoming video, we'll explore Fortran and the program for matrix multiplication. I am looking forward to the next video. Wishing you all happy computing in the meantime.